Hello everybody. This video is prompted by a user question. They asked about what happens if you have a finite group with exactly two maximal subgroups. And so I want to show in this video that any such group is cyclic. So let me start with an example. So let's take the cyclic group of order 6. So this might be generated, say, by some element z of order 6. And so if I look at z squared, I'm going to get a cyclic group of order 3 inside this group of order 6. If I look at z cubed, I'm going to get a cyclic group of order 2. And then, of course, I have the trivial subgroup at the bottom. Now, these are the only subgroups of C sub 6. And what you can see here is that C3 and C2 are proper subgroups, but they have no subgroup in between them and the entire group. So we're going to write down here the definition then of a maximal subgroup based on this. So a group, or I should say a proper subgroup of a group is maximal if no proper subgroup of, well, let's see, we'll give a name. Maybe this is a group G. No proper subgroup of G, and maybe, okay, a proper subgroup M. Fine. If no proper subgroup of G properly contains M. So pictorially, we have a group G, and maybe we have some subgroup M, and we're going to say that M is maximal if there's no way to put a subgroup in between. All right, so I would need a proper subgroup, so meaning smaller than G, that properly contains M. So M is strictly smaller than that group. So if this dot here is not possible, then M is supposed to be maximal. So you can see over in our example, C3 and C2 are maximal because first they're proper, and there are no proper subgroups in between them and the entire group. And you can see in this example, we have exactly two maximal subgroups. And so what I want to prove in this video is that whenever you have a finite group with exactly two maximal subgroups, it must be in some comparable situation, namely, you must be working with a cyclic group. All right, in order to prove this, I need a couple of lemmas. These are not obscure things. These are things you very likely could have seen in your introductory group theory course. So let's start with lemma 1. So lemma 1, we're going to say if I have a non-trivial group, so G is not the trivial group, then every proper subgroup of G, which is possible because G is not the trivial group, every proper subgroup of G is contained in a maximal subgroup of G. All right, so let's do the proof. All right, and of course, I'm working with finite groups everywhere in here, so I mean, I could say this in here, so G is finite. And so the way I'm actually going to do this is by induction on the index of the proper subgroup that I have. Okay, so let's let H be a proper subgroup of G. Remember, this notation means it's a subgroup and there's no line underneath, so it's really a proper subgroup. So it's not equal to G. All right. So we will prove the result by induction on the index of H and G. Okay, which you'll recall by Lagrange's theorem is the ratio of the cardinality of G to H. All right, now there's kind of a silly inductive base case All right, so you might say, okay, well, base case usually is 1. So let's look at that base case where G and H, right, have the index of H and G is 1. Well, that would happen, right, only if H is equal to G, which actually contradicts the assumption that H is proper. So this may be not the best base case. Okay, so this situation just can't happen, right? So let's do a different base case. How about if the index was equal to 2, right? Let's check what happens in that situation. So in this situation, what could we do to put a group in between H and G? So if H is a proper subgroup of K, and K is a proper subgroup of G, then I claim we're going to have a little problem with Lagrange's theorem here. So we know that the index of H and G is 2. But the index of H and G is equal to the index of H in K times the index of K in G. And so I now have that 2 can be written as a product. But 2 is a prime number. These are positive integers. So the only way this can happen, right, is if one of these numbers is 1 and one of these numbers is 2. Well, whichever one of them is 1, that would tell you that if the index is 1, then just like in this base case up here, then the groups are equal. That would tell you H equals K or K equals G, which would be a contradiction. So it is impossible to have some K in between H and G. So there is no proper subgroup of G that properly contains H. And so this tells you that H is maximal in G. Okay, so cool. We have a base case that you might believe. How about the inductive step? So assume that every proper subgroup of G of index less than the index of H and G is contained in a maximal subgroup. Okay, so that's our inductive assumption. And so now we want to show that H itself is contained in a maximal subgroup. Right? Well, first, H could itself be a maximal subgroup. Right? So if H is maximal, well, it's contained in itself, then we're done. Okay, fine. So what if H is not maximal? If H is not maximal, then it is contained properly in a proper subgroup. So then there exists some K properly contained in G, but properly containing H. Okay, but this now tells you then that the index of K in G, well, if we look up above, right, we actually know we have this nice relationship up here. The index of K in G is actually equal to the index of H in G divided by the index of H in K. Okay, but we know that the index of H and K is not equal to 1 because H is a proper subgroup. So this number down here is greater than 1. And so you're taking a number, the index of H and G, and dividing it by a number bigger than 1. And so you must be strictly less than the index of H and G. So K is a subgroup whose index is less than the index of H. But every proper subgroup of G whose index is less than the number of the index of H and G is contained in a maximal subgroup. So this implies that K is contained in a maximal subgroup. right? This is by induction in a maximal subgroup. Oh, but H is contained in K, so H is contained in a maximal subgroup. So this implies H is contained in a maximal subgroup. And that finishes the proof. Right? If H was maximal, we're done. If H is not maximal, we proved it's contained in a maximal subgroup by induction. All right, so this is wonderful, right? We have a finite group. It's not trivial. We take any proper subgroup and we just say, well, it's contained in some maximal subgroup. All right, that's going to be useful. Lemma 2. So lemma 2 is that, and this really is not even dependent on having a finite group. So if H and K are proper subgroups of G, okay, so they're not equal to G, then G does not equal the union of H and K. It is just simply impossible to write a group as a union of two proper subgroups. All right, so let's do the proof. This is actually fairly straightforward a proof. So let's prove this by contradiction. Okay, so we're going to assume G is equal to the union of H and K. So first, what if H was a subset of K? If H is a subset of K, then the union of H and K, well, H isn't adding anything new, so the union is just K again, which is a proper subgroup of G, and this contradicts the assumption that G is equal to H intersect K. All right, so we can conclude H is not a proper subset, or rather a subset at all of K. Of course, the exact same argument shows, right, that K is not a subset of H. So similarly, K is not a subset of H. So what this means is that there is something in H that is not in K, and there is something in K that is not in H. So let's give names to a couple of elements then. So let little h be an element of H that is not in the group K, and let's let little k be an element of big K that is not an element of H. And now let's look at the product of little h and little k. So we have little h times little k is certainly an element of G, right? G is a group, it's closed under product, so that's not a problem. So this is an element of G, but G is equal to H union K. So that means that HK, this product, is either an element of H or an element of K or both even. Let's show that that's not possible. So if little k is an element of H, big H, then we would get that little k is an element of H inverse times H. But of course, H inverse is an element of H. And so this coset is actually just equal to H. And this would tell you that little k is an element of H. But our assumption was that little k is not an element of H. So this is a contradiction. Of course, the same proof is going to work if we assume that little hk is an element of big K. In that case, little h is an element of K times little k inverse, which is again equal to K. And so h would be an element of K, but again, we assumed little h was not an element of K. So again, we get a contradiction. So this whole thing shows us that this element hk, which is an element of G, and so should be in H or in K, is not in H or in K. And so this entire setup is a contradiction. And that contradiction comes from the assumption that G can be written as the union of two proper subgroups. Okay, so that finishes the proof of the lemma. And now we can get to the main result. Okay, so theorem. A finite group with exactly two maximal subgroups is cyclic. So we've already seen, of course, examples where a cyclic group can have exactly 2. So we're going to prove this by assuming we're in a situation of a finite group with exactly 2 maximal subgroups that is not cyclic. So let G be a finite non-cyclic group with exactly 2 maximal subgroups. Now let's just call them, say, M and N. All right. I'm going to choose some element from the group. Okay, so I take some element X in G. X, of course, generates a cyclic group. And because G is not a cyclic group, the group generated by X cannot equal G. So as G is non-cyclic, G does not equal the subgroup generated by X. So that tells you that the subgroup generated by X is a proper subgroup. So by lemma 1, the group generated by X is contained in a maximal subgroup. And we all know there's only 2 maximal subgroups, M and N. So this group is contained in M, M or N. And so in particular, right, so this tells us, this implies every element of G is contained in, well, it's contained in the group generated by that element, which is contained in either M or N. So that element is contained in either M or N. Oh, but if every element of G is in M or it's in N, this implies that G is the union of M and N. Every element in G is certainly in that union. But this is a contradiction to lemma 2. Right? So this contradicts lemma 2, since M and N, being maximal subgroups, are proper subgroups. And it is impossible to write your group as a union of 2 proper subgroups. So that's it. That's the entire proof. So there's more work done, right, in the lemmas, right? That's great. All right, so this was a really fun problem. Thank you for asking it. Look forward to solving more of your problems in the future. We'll see you next time.